sensor up here. When I break the beam, fires a solenoid that drops Buster on his own weight.
Buster's full weight will be on his feet each time he's clobbered. So, seconds out, it's round one, the uppercut.
We're about to knock you out.
Last time we pulled out Nitro Punch and gave Buster a really good uppercut, we almost knocked his socks off, and that was with a tight sports sock. Now we're using this woolen hand knit sock. I think this might actually work.
Well, there's only one way to find out.
500 PSI, we're good to go.
All right.
Okay, this is uppercut with proper socks and legs.
All right. Fight.
All right, here we go. In 3, 2, 1.
What happened?
Wow. We knocked him out. I can't tell if his socks came off or not.
That punch just landed a massive 6,000 Newton uppercut straight to Buster's chin. That's twice the force of a heavyweight boxer.
We stone cold knocked him out, but his socks are still on. They are not coming off. No matter how much force is hitting him, the socks are staying on. It looks like this is not the punch.
Despite all the fan-inspired changes, the uppercut didn't cut it. But there's more bare-knuckle action to come.
Coming up next on Mythbusters, find out what kind of force it takes to knock your socks off.
No,
It didn't work before, it didn't work this time.
but the Mythbusters aren't throwing in the towel yet.
And that's because the fans think we have two other kinds of punches to try, the right hook and the body blow. We'll be testing both of these punches with robots because they have superhuman strength. And if they can't knock the socks off, they'll never get punched off. But we're gonna start out by getting hooked.
In the sweet science of bruising, a right hook packs a powerful punch. By pivoting as he swings, a boxer drives the force of the blow across his opponent's body. It's this transverse momentum that could focus the friction to force the feet from the socks. For round two of punching, it's Buster versus the right hook.
So, gentle viewers, to address your very important concerns, I've built this incredible punching robot that simulates a right hook.
And these are the hand-knit wool socks that have the least resistance, and they are over our human-like feet.
And this is our quick release and laser trigger. So just before impact, it will release Buster so he's standing on his own weight, just as you requested. We're ready to go.
Fight! All right, here we go. In 3, 2, 1.
Wow.
Wow.
We knocked him over, but look, his socks are still on.
One massive right hook to the head, and the force is enough to knock Buster sideways, but not his socks.
That punch was incredible. I mean, the power, bang! And Buster actually did a somersault. However, did not knock his socks off. But Buster has one heck of a chin. Looks like he wants to go for another round.
And for the last round, the team have the most powerful punch yet, the body blow.
Now, our body blow machine is the most powerful one we have, and that clocked in at 52,000 newtons, or 15 times your average boxer.
That massive momentum will be delivered right into Buster's breadbasket.
This is Knock Your Socks Off, straightforward body blow. We have knit socks, leather legs, and Buster on his own weight, 180 pounds.
Fight! All right, here we go. In 3, 2, 1.
Whoa! We knocked him out, but still, his socks remain on.
Although there was some encouraging sock movement, even a punch 15 times that of a heavyweight boxer couldn't separate Buster's legs from his socks.
So, the myth that you can punch someone out of their socks is busted. The uppercut couldn't do it, the right hook couldn't do it, even the super body blow could not do it. They all failed, even using the socks that were the easiest to come off. But don't worry, we're not gonna give up. We're gonna keep trying. Ugh.
After the break,
Let's go twice as fast.
Adam and Jamie drive another car up the wall. Game of physics.
How did we get here? Well, It all started when Jamie said this.
Both trucks were traveling at about 50 miles an hour. That's equivalent to a single impact going into a solid wall at 100 miles an hour.
That's pretty sound reasoning for my money, but no, the fans cried. 2 cars hitting each other at 50 miles per hour do not equal 1 car hitting a wall at 100 miles per hour. Because their masses is the same, they cancel each other out, and it's no different than 1 car hitting a wall at 50 miles an hour. I find this surprising and hard to wrap my head around, but our scale experiments seem to bear it out. But of course, we're not going to leave it there.
This is what happens when you crash a car into a wall at 50 miles an hour. Next up, we're going to be crashing a car into a wall at 100 miles an hour. How bad will it be? We're just going to have to crash it to find out.
So an identical car, well, except for the fact it's lemon yellow,
That's good. Bring it straight in.
is hooked up to the track.
All right.
Now, the 50-mile-per-hour impact clocked an impressive 58 Gs. But will doubling the speed double the damage to this car?
It's good. I gotta say that after watching that 50-mile-an-hour crash into the wall, I have a really hard time imagining that the 100-mile-per-hour crash is gonna compress the car that much more. I don't know.
So are you ready for some more wanton destruction?
I am! Let's go twice as fast.
All right.
Wanton destruction it is, as the Mythbusters retire to a safe distance and the countdown begins.
You ready to make this happen?
I can't wait. I haven't seen a 100-mile-an-hour crash before.
No. All right, commence with the 100-mile-per-hour crash.
On Adam's command, the engines whir into life, straining to get the car up to exactly 100 miles per hour. It hurtles down the track.
It's going flat out.
The cable uncouples, and the car plows into its final destination. The guys are understandably speechless. That impact crushed the lemon car with such force, it should be in a glass with ice and a cocktail umbrella.
It's in a very different state than it was at 50 miles per hour.
Yeah, it's a little shorter.
I mean, we got a clear difference between the 2 crashes.
Uh-huh.
I can't wait to see what the data set says about the G-load.
If the data's still intact.
If anything's still intact.
Well, thanks to its position in the trunk, the black box survived.
So did we successfully retrieve anything?
We've got good data.
Really?
Yeah, we've got a peak on the left side of 140 and a peak on the right side of 230. And we'd normally just average those to get a resultant there.
So the midpoint's somewhere around 185?
185.
That's nice. That's significantly more than, what was the last one, 58?
58.
Data!
3 times the G's of the 50-mile-per-hour test is certainly significant. But that's not the only data set they're collecting.
Before it was 15 feet. Now it's 8 feet.
So not only did the G-load triple, the crash compacted almost half of the car. And remember, these 2 cars were identical.
This may just seem like some gratuitous violence, but there's actually some really interesting science going on when you compare these 2 impacts. You would think that doubling the speed would give you twice the severity of the impact, but the physics says you're actually looking at more like 4 times the severity of the impact. Our sensors are showing 3 times the G's, and our wreckage is showing about twice the damage. So what's going on here? Well, just like this can, the more I crush it, the more it resists crushing. There's some complex physics going on here, but you don't have to be a rocket scientist to understand it. The cars speak for themselves.
They certainly do. And after 2 spectacular crashes, they have their benchmarks for car carnage.
Well, we've got our data points.
And they are lovely. I guess it's time to move on to the main event.
Yep.
Next up,
Hold on to your socks, Buster!
the Mythbusters think outside the boxing ring.
boxing ring, we're gonna see some results.
Yeah, but last time we ramped this up, we used that frightening huge pendulum, and we still got nowhere.
You know, that's another fan complaint. Here, listen. Your pendulum hit Buster at a lower speed than your punching rig, so this test was actually a ramp down rather than up.
Yeah, but it did weigh a lot more.
True. But you know what? To directly address that concern, why don't we increase both the mass and the speed?
Okay, how about this? Big steel girder. We